Okay, so let's move on now to, what time is it? Okay, so let's move on now to postulate 4. Okay. Quantum mechanical operators representing system properties have a complete orthonormal eigenbasis. An eigenbasis is just a set of eigenfunctions. Okay, so in other words, if you have a quantum mechanical operator that you're using to represent system properties, then you have to postulate, we have to assume that it has a complete set of orthonormal eigenfunctions. So its eigenfunctions, if you list all its eigenfunctions, you can find a set that forms a complete set. What do we mean by a complete set? Remember we talked about a complete set last time? That means, what that means, okay? Any wave function, psi, that you can use to describe the system can be written as a linear combination of those eigenfunctions. So f1, f2, f3, and so on are eigenfunctions of your operator. Then you can write psi as c1 f1 plus c2 f2 plus c3 f3 and so on. Okay? And so that, and not only that, the probability of obtaining eigenfunction a sub I, okay, we're defining a sub I here is as the eigenvalue, eigenvalue. We're defining a sub I as the eigenvalue corresponding to f sub I. So if I have a hat, operator A, I'm interested in property A, okay? The property I'm interested in is A. The operator is a hat. If I were to operate on an eigenfunction of a hat, let's say f sub I, then I'm going to get back a sub I times the original eigenfunction f sub I, okay? So this little a sub I is the eigenvalue. What we're saying in this postulate is, remember we said if we measure A, the only possible outcomes are the eigenvalues, a sub I, right? A1, A2, A3, and so on. Now the probability that you're going to get a sub I is given by this, the square of this expansion coefficient. So c sub I squared, absolute value of c sub I squared, which we've already shown before is just going to be equal to integral of f sub I star psi theta, or this one. That's your c sub I. Okay, now let me just refresh your memory with that one. Okay, let's see. What happens if we take integral, for example, of f2 star psi theta? Just for example, what do you get? Integral of f2 star, and what's the expression for psi? c1 f1 plus c2 f2 plus c3 f3 plus, and so on and so forth, theta, right? So what do? Distributive property, I can distribute this, right? So this is going to be integral of f2 star c1 f1 deta plus integral of f2 star c2 f2 deta plus so on and so forth, right? And what can I do with this at this point? Constant can be pulled out of my integral, right? So this is going to be c1 integral of f2 star f1 deta plus, I pull this one out, c2 integral of f2 star f2 deta plus, and so on and so forth. What is integral of f2 star f1 deta? Your indices, you have two different orthonormal functions. 0. Why is it 0? Because we say f1 and f2 are orthogonal. Okay? So this is 0. And what is f2 star f2 detail? 1, because we say that your eigenfunctions that we've chosen a set of orthonormal eigenfunctions, right? So each function is orthonormal. So what are all the other values going to be? All these extra terms here. It's going to be 0. So here you just end up with what? C2 times C2. Right? So you can see that C2 is just integral of f2 star psi theta. So in general, C sub I is going to be integral of f sub I star psi theta. Or you can write that in bracket notation. Makes it easier. Okay, so the probability that if you were to measure particular property A, okay, according to postulate number 2, the only values, postulate number 3, the only possible values you can get are A1, A2, A3, A4, those little a's, right? The eigenvalues. This postulate says what? The probability that you would get any one of those particular values would be equal. It would be equal to the square of the coefficient in the expansion of psi in terms of the eigenfunctions. Okay? So let's illustrate that with a simple example. Let's say A hat, okay, the eigenfunctions of A hat are f sub j, where A hat f sub j gives you back j times j plus 1 times alpha times f sub j. You notice, okay, alpha is a constant, okay, and j is 1, 0, 1, 2, 3, and so on. So what is f? What would be, for example, if I were to do A hat f0, what would my eigenfunction be? What is our j this time? J equals 0. So I get back the eigenfunction times f0. What goes here? What is j? 0 times 0 plus 1 times alpha. What is 0 times 0 plus 1 times alpha?
0.
That's 0. Okay. What about A hat f1 is equal to a constant times f1. What's the eigenvalue here? Remember, our eigenvalue is j plus 1 alpha, right? So what would this be? 1 times 2 times alpha. So in other words, we're saying A hat f1 is going to be 2 alpha, right? And A hat f0 is going to be 0 times 0. I'm sorry. This is 2 alpha times f1. And A hat f0 is 0 times f0. Okay, what's A hat f2 going to be? Something times f2. 2 times 2 plus 1, which is 3 times alpha. So it's 6 alpha. So you say A hat f2 is equal to 6 alpha f2. See the pattern? So what are the allowed values of property A? So based on this, what's the lowest allowed value of A? 0, right? So allowed A's would be A0, A1, A2, A3, and so on, right? What is A0? 0, right? What is A1? 1 times 2 alpha, so it's 2 alpha. What is A2? 2 times 3 alpha, that's 6 alpha. What is A3? 3 times 4 alpha, so 12 alpha, and so on. Okay, so if I were to ask you, what's the probability that if I made a measurement of A, I'm going to get 3 alpha? Is 3 alpha allowed? No. If it's not allowed, what's the probability I'll get it? 0. Okay? What's the probability that if I measure A, I'm going to get 7 alpha? 0. Okay? What's the probability that I'm going to get 2 alpha or 6 alpha or 12 alpha? Then I have to know what psi is. See? Psi gives you all the information that you need. all the accessible information. So if I want to know what's the likelihood I'm going to get 6 alpha if I were to make this measurement of A, then you say I have to know what psi is. Okay? And so let's say in this example, what if psi is given by this? 1 over square root of 6 f1 plus 2 plus 3 plus f3. Let's rewrite this. As C1 F1 plus C2 F2 plus C3 F3. What would that be? 1 over square root of 6 F1 plus 2 over square root of 6 F2 plus 1 over square root of 6 F3, right? Okay. What is A1? What did we say A1 was? 1 times 2 alpha. 1 times 2, so it's 2 alpha, right? So what's the probability that I'm going to measure A and I'm going to get A1? It's going to be, according to the postulate, it's going to be C1, absolute value of C1 squared, right? What is my C1? 1 over square root of 6. So C1 F1, C2 F2, C3 F3. So it's going to be 1 over square root of 6 squared, 1, 6. In other words, imagine you have billions of these identical systems. Okay? They're identical, but if you measure, they have the same size. But if you measure A here, you measure A here, you measure A there, okay? 1 out of 6, you're going to get 2 alpha, even though they all have the same size. Right? So 1 out of 6 chance that if you measure it for this particular system, then you get 2 alpha. Right? What's the probability that you're going to get A2? What's A2? 2 times 3, so that's 6 alpha, right? So what's the probability that if I measured A, I'm going to get A2? Then it's just going to be coefficient 2 squared. What's the coefficient of F2? 2 over square root of 6 squared, which is 4/6. Okay? What's the probability that I'm going to get A equals A3? What is A3? 3 times 4 is 12 alpha. So it's going to be what? C3 squared. Right? Probability that I'm going to get the eigenvalue, the third eigenvalue. It's just the square of the third coefficient. That's the third coefficient. 1 over square root of 6. You square that, you get 1/6. What's the probability I'll get anything else? All the other coefficients are 0, right? So even though, so what did we say this one? 2 alpha, you have a 1/6 probability. 6 alpha, you have a 4/6 probability, right? And 12 alpha, what's the probability? 1/6. 0 is allowed, according to this, but what's the probability I'm going to get 0?
0.
In this particular specific case, it is 0, because C0 in this case is 0. Yeah. So J equals 5, what's 5 times 6? That's 30, right? So what's the probability I'm going to get 30 alpha? 0. Even though it's allowed, in this particular case, because C5 is 0, probability of finding 30 alpha would be 0. That's what it means. Okay? So that's postulate number 4. Okay. So this is the same thing we looked at earlier. So you have to imagine a very large number of identical systems, okay, where A hat Operator A hat gives you j plus 1 alpha times f sub j. So f sub j, we say, if the eigenbase is the orthonormal eigenbasis of operator A. And then psi is equal to 1 over square root of 6, f1 plus 2, f2 plus f3. So if property of A is measured, what's the percent of the system that will give, what percent of the system will give you 6 alpha? 6 alpha is what? 2 times 3 alpha. So that means that's A2, right? So it's going to be, the answer would be C2 squared is the probability. Right? So it's 2 over square root of 6 squared. That's 4, 6. So 2/3. So what percentage? 66.7%. Okay. Okay, same system. What's the probability you're going to get 12 alpha? That's the eigenvalue of F3. We already, what was it? 1/6, which is 16 point something percent.